Okay, so now we come to Chapter 9. Chapter 9 is a very fundamental chapter in the course book in its content of statistical ideas. So we're going to talk about both estimation and hypothesis testing. So the learning objectives are to understand how to test hypotheses and to estimate population characteristics using statistics. So if we're thinking about estimating means or proportions, we are starting from this idea of representativeness. So if the sample is representative, then we can assume that our sample will on average be similar to the population. So for example, the sample proportion should be a good estimate of the population proportion, so that the sample proportion of, say, males times the population size should be a good estimate of the population size of males. Now, this idea only works if the sample is representative. So, for example, if all individuals have equal chance of selection and they all have even if their chances are not equal, if individuals have non-zero chance, then we can still adjust the weighting of the respondents so that we can still have a good estimate. So in other words, we can account for non-equal chances of selection as long as we know what those non-equal chances are. We can also critically provide an idea of how accurate our estimates are. So in other words, it's not just are our estimates good on average, but do we know how good they are? So we're going to look at an example first before we go into these concepts formally. We're going to start by an example. Let's say we drew a random sample of 1,000 school children in Hong Kong, and of those 1,000 children we observed 520 boys and 480 girls. So what can we then say about the proportion of school children in Hong Kong as a whole who are boys? Obviously our best estimate is going to be the sample proportion, which is 520 over 1,000, in other words 52%. But how accurate is that estimate? That's not at all obvious, right? Obviously, if we drew a sample of the whole population, there would be no sampling variability left. So let's simplify things for the moment. We're going to assume that the total number of children in our population is much greater than 1,000. As I said, if the population size is only 1,000, then our estimate would be exact. So in most situations where we're drawing samples, our sample size will be less than 1% of the population size, and we don't have to worry too much. It turns out that the population size doesn't matter unless it's relatively similar to the sample size. So if the sample size is more than 1% of the population, we would need to make an adjustment, and we'll talk about that later. In other words, the estimate will actually be more accurate if the population size is not that much bigger than the sample size. So the jargon we use for describing the accuracy of our estimate is we say that the approximate 95% confidence interval for the population proportion is 52% plus or minus twice the square root of 52% times 48% over 1,000. So in other words, the formula for this approximate answer is p plus or minus 2 times the square root of p times 1 minus p over n, where p is the population proportion and n is the sample size. So this approximation is quite good as long as the sample size is not too small, meaning the sample size is at least 30 is usually our rule of thumb, and that the sample proportion is not too close to either 0 or 1. Otherwise, we need to use more exact methods that we will talk about later. So, if we apply this formula I just showed you, we get that the answer is 52% plus or minus 3.2%. So our interval contains values from 48.8% up to 55.2%. So what does this thing 95% confidence interval mean? It means that on average, if we drew a large number of samples, then in about 95% of our samples, our confidence interval would contain the population proportion. Now, this is quite a hard concept because this is not a probability statement about our specific interval, but instead what would happen if we repeat our sampling. Because remember, probability is about long-run relative frequency. So whether a particular interval contains the value is either true or false, right? So the probability meaning is if we drew repeated samples. So we'll come back to these ideas much more carefully later on and explain where this formula comes from. But the key idea is the confidence interval is based on the assumption that we do repeated samples, and then across these repeated samples, how often does the confidence interval contain the true value? So that's one way to think about things, but the other way is to think about it in terms of hypothesis testing. So for example, if we wanted to test hypotheses about the proportion of male and female in the population, so for example, if our concern is about whether there's a sex imbalance in the schools, clearly in that situation the null hypothesis would be equal proportions of males and females. There are three different possible alternative hypotheses. The complementary one is just simply males and females are unequal. But we can also have what we call a one-tailed alternative, where we're really only interested in whether males are more than females or whether females are more than males. So let me explain a little bit about the context. So interestingly, the Equal Opportunities Commission in Hong Kong took the government to court not too long after Hong Kong first introduced discrimination laws. And actually it was about unfair procedures for school allocation. So historically, Hong Kong used to have a system for deciding which primary school students got into which secondary school students based on the performance of those students in a public exam in primary school, right? That's how it used to work. So the Equal Opportunities Commission took the government to court for being in breach of the discrimination law. So it's actually quite an interesting conceptual question. What is fair or what is unfair in terms of allocation of places? So for the moment, let's ignore the issue of single-sex schools. So let's just assume that all the schools are co-educational, right, except both boys and girls. So the problem was that the system the government used to use worked something like this. The idea was that they had the concept that there should be equal numbers of boys and girls in all the schools which were competitive. And so the government had different cutoffs for boys and girls to get into a school. So if we consider an elite school, which everybody wants their child to get into, the government would allocate equal numbers of boys and girls places. So what's the problem with that? Well, the problem was that generally girls were performing better than boys on this test. So that meant that in practice, girls had to score higher than boys in order to get into these schools that were most competitive. So if you look at the way the law is framed, it's very clear that that is discriminatory and it's illegal, right? So in other words, you should be choosing the same cutoff for boys and girls. Now, of course, you might beg the question, is there some reason why girls perform better than boys on this test? And in fact, boys and girls do not develop at the same rate throughout their lives. Girls go through pubescence younger than boys, and in fact, also girls overall tend to perform better on language-related testing than boys do. So one could argue that the real fundamental problem was that the test itself was problematic. But the government had never bothered to look at that. They had just simply said equal numbers of boys and girls in the schools, If that means that girls have to perform better than boys to get in, that's just bad luck. So it's a different concept about what fairness means. Does fairness mean equal numbers of boys and girls get put into a school? Or does fairness mean that you should have the same cutoff? And of course, implicitly meaning that the test should be equally difficult for boys and girls. Anyway, so this is just showing you that actually equality or fairness between males and females is not always an obvious question. It can depend on what you mean by fairness and how you're going to evaluate whether you have a fair system. Okay, so come back to our problem. So we're going to look at the simpler alternative first. In other words, just simply males and females unequal. Because in fact, if you look at the law that I'm just talking about, it simply says there should be no discrimination between males and females. It doesn't say no discrimination against females, right? So it's in theory possible to use the law if you felt that males were being discriminated against, right? So the real question is, are they different? So we're going to look at the null hypothesis versus the complementary alternative of males and females unequal. So the question is, does our sample provide any evidence that our null hypothesis is false? Right, so as I said to you before, we often cannot disprove our null hypothesis, but we may be able to provide evidence against our null hypothesis, and so we need a comparison point. So our comparison is relative to the alternative that males and females are unequal. So how are we going to do this hypothesis test? So the fundamental idea is that we want to find a good summary of the data that best summarizes the evidence for choosing between the hypotheses. So this summary is called our test statistic. So in this case, we can prove that the sample proportion is the best test the best test statistic. If the test statistic has a value that is unlikely to occur if the null hypothesis is true, then we will reject the null hypothesis. So strictly speaking, nearly all values are unlikely to occur, right? Remember, if we have a sample of 1,000, there are 1,001 different possible sample proportions. So all of those sample proportions will be relatively unlikely. So actually what we mean is this value or more extreme values are unlikely, rather than just that one value is unlikely. So how do we implement this idea? Well, first of all, we need to find the probability of observing the test statistic or a more extreme value if the null hypothesis is true. And if this probability is sufficiently small, we will reject the null hypothesis. So what does sufficiently small mean? What is our cutoff value? This is what we call the significance level, right? So if this significance level is small enough, then, and we get a probability less than this, then we will reject the null hypothesis on the grounds that what we observed is not consistent with the null hypothesis, okay? So what about this situation here? Well, it turns out that the probability of observing a sample proportion of 52% or a more extreme value, if the population proportion is really a half, is about 20%. So that means the probability of getting 52% or more, or equivalently in the opposite direction, 48% or less. So there's about a 20% chance, if we did many samples, that so we're saying in about 20% of our samples, if we drew a large number of samples with a population proportion of 50%, about 10% we would get 52% or more, and about 10% we would get 48% or less. So put those two together, there would be a chance of about 20% of getting a result like this. And usually we wouldn't consider that to be sufficiently small. So the cutoff values we generally use are either 5% or 1%. So that means we're choosing to accept the risk of rejecting the null hypothesis when it's really true, either about 5% of the time or about 1% of the time. So which significance level we use as a cutoff value depends on what risk we're prepared to accept for making the mistake of rejecting a null hypothesis which is really true. Okay, so we'll come back to these ideas much more carefully later on. But let's go back a stage. We said before that probability tells us, given a population, what sorts of samples might we expect to get. So if we know what the population is like, what can we say about the samples? Well, it turns out that we can show that for a probability sample, the average of the sample means tends towards the population mean as the sample size increases, as long as we have a probability sample. In fact, we can show that for a probability sample, the average of all possible sample means is the population mean. So we call this property unbiasedness, meaning that on average we get the correct answer with no bias. Okay, so that's about the sample mean. What about the variance? Well, it turns out that the sample variance is quite a good estimator of the population variance as long as the sample size is not too small. So generally we'd accept that if the sample size is at least 30, the sample variance is a good estimator of the population variance. Now we need to introduce one more concept. This is what we call the standard error. So the standard error is the standard deviation of the distribution of the sample mean. So if we do repeated samples, the standard error tells us how much variability we expect to find in the sample mean. So clearly, if the sample size is large, the standard error should get small, right? Because we've got a bigger sample, there should be less sampling variability. So it turns out that the standard error we can prove is the population standard deviation divided by the square root of the sample size. So remember, this means, of course, if we have a sample of 1, the square root of 1 is 1. So clearly, if we draw a sample of 1, the standard error is just the population standard deviation. That's obvious. We're just drawing a random individual. But as the sample size goes up, this tells us how the standard error decreases. It says it decreases proportional to the square root of the sample size, right? Now, I said before we're assuming that the population size is much bigger than the sample size. Otherwise, we need to introduce a correction factor. So that correction factor is 1 minus the sample size divided by the population size. So in other words, if the sample size is equal to the population size, the correction factor is 0. There is no variability, right? There is no variability left. If the sample size is small compared to the population size, the correction factor is very close to 1. So we can ignore this. So that's why I said if the sample size is less than 1% of the population size, we can ignore the correction factor because it means the correction factor is at least 99%. Okay, so what about the sample mean? So it turns out that the distribution of the sample mean, we can actually say something about the approximate distribution of that sample mean. It's approximately what we call a normal distribution with a capital N, meaning a known probability distribution, as long as the sample size is not too small. So if the sample size is greater than about 30, almost regardless of the original distribution, the sample mean has this approximate distribution. Now that's really quite amazing, right? It says it doesn't really matter what the original distribution is, as long as our sample size is big enough, the sample mean converges on the same distribution. So you'll see that I've got a footnote here saying that independent, identically distributed data with finite variance is a sufficient condition for this. So I'm not going to go into this in detail. We are generally talking about independent, identically distributed samples. Finite variance just means that the variance must not be infinite, right? So in any practical situation, the variance will be finite. So this is generally going to be true for any practical situation most of us will consider. Now, this is the amazing thing. So none of these statements require us to know the full distribution of values in the population. So only if we have small sample sizes, then the population distribution becomes important. In those situations, we need to do some checking to see whether our approximation is okay. So we're going to show, so I'm not going to show any mathematical proofs. I'm going to show you an empirical verification of what we've just said. We're going to do this through simulation. So I got the computer to do 5,000 simulations for me of a number of different experiments so that we can see how this works in practice. So we're going to start out with a fair coin, meaning the probability of head or the probability of success is 50%. And we're going to look at the histogram and the box plot for the proportion of heads in these 5,000 simulations if we do one of 4 different experiments. So our first experiment is where we just do a single toss. Our second experiment is 10 tosses in each experiment. Our third experiment, we do 20 tosses in the experiment. And our last experiment, we'll do 80 tosses in each experiment. So let's have a look at what we get. So I want you to look at the first row here. We'll talk about the second row later on. So in the first row, we start out with 1 toss. So 1 toss is actually not interesting at all because from a single toss, we either get a head or a tail. So 1 single head, the only thing we can say for sure is it's not a 2-tailed coin. And if we get 1 tail, the only thing we can say for sure is it's not a 2-headed coin. Right? We can't draw any useful conclusions from a single toss. Now, look at the second column. So this is showing you the results if we do 10 tosses. It's showing you both the histogram and the bar chart. So you will see that we did occasionally get all heads and we did occasionally get all tails. Not very often, we do occasionally get that. But you can see the most common outcome is half heads and half tails, meaning 5 of each. And you can see that most of the time we're getting somewhere between 20 and 80% heads, right? But we do occasionally get all the way down to all heads and all tails. So let's just think about this for a minute. If you do 10 tosses, what's the chance of all heads or all tails? So that's a half to the power of 10. So half the power of 10, right, if you work that out, it's roughly 1%, right? So if we think back to this, we said we did 5,000 simulations. Sorry, a half to the power of 10 is 1 in 1,000 roughly. Sorry, not 1 in 100, roughly 1 in 1,000. So it's about 0.1%. So with 5,000 tosses, we would expect to get about 5 times to get all heads and about 5 times to get all tails on average. Right? It won't be necessarily exactly 5. So it's a relatively rare event, but we would get it. Now let's consider 20 tosses of a fair coin. By now, that means the chance of getting all heads or all tails is 1 over 1,000 squared. So it's about 1 in a million. So it's not very likely. And in fact, you can see the smallest proportion we got was 10% and the biggest was 90%. Right? So we always got at least 2 heads out of 20 tosses, and the maximum we got was 18 out of 20. So if we look at this, you can see that most of the time we're getting between 30% and 70% heads. Again, the most common outcome is 50%. Okay? Now, what about when we go up to 80 tosses? So by the time we got to 80 tosses, you can see that the histogram has this sort of bell-shaped curve. So this bell-shaped curve is characteristic of what we call the normal distribution with a capital N. And by the time you get to 80 tosses, you can see most of the time we're getting between 40% and 60%. So if you think about it, that means that the spread, right, we were getting a range of 30 to 70% with 20 tosses and 40 to 60% with 80 tosses. So the spread has shrunk by a factor of 2. And that's exactly what we would expect to occur, because I said that the standard error, right, depends on the square root of the sample size. So if the sample size has gone from 20 to 80, the square root of 80 is twice the square root of 20. So we would expect that the standard error should have decreased by a factor of 2. In other words, the spread should have decreased by a factor of 2, and that's exactly what's happened. Okay, so empirically we've seen that indeed the spread does shrink by a factor of 2 as we increase the sample size by a factor of 4, and also that if the sample size is bigger than 30, we get a very nice approximation to this bell-shaped curve. Now, this is perhaps one form of verification, but let's consider another situation, right? So we're now going to consider a more tricky situation. We're now going to consider an unfair coin to see what happens now, because you might think tossing a fair coin is already symmetrical, so it's not too surprising that we get some form of a symmetrical distribution for the sample proportion. But now we're going to consider an unfair coin which has a 70% chance of getting ahead. So this is the second row. So again, one toss, not really very interesting, right? Just that on average, we'll get 70% head and 30% tail. So it's still representative, but it's not very helpful. So when we look at 10 tosses, you can see the distribution is still quite asymmetrical. And you can see that it's not too rare for us to get all heads, right? But we never got all tails. Okay, so we have biased the coin enough that we never got all tails. But we still, on average, the most common outcome is 70%. Now, by the time we get to 20 tosses, you can see the distribution is already quite symmetrical. Right? Even 20 tosses is quite symmetrical, and we're getting a spread that goes from roughly 0.5 to 0.9. Okay? So centered on 0.7, and most of the time we're getting values between 0.5 and 0.9. So now when we go up to 80 tosses, again we get this nice symmetrical curve. You'll see the shape of this curve is very similar to the shape of the 80 tosses with a fair coin, but instead of being centered on 50%, it's centered on 70%. And again, the spread has shrunk by a factor of 2. Instead of going to 0.5 to 0.9, we're now doing 0.6 to 0.8. Okay? So we can again see that as we increase the sample size by 4, the spread shrinks by a factor of 2. And again, we can see that with large enough sample sizes, then we get this approximate bell-shaped curve, even though the original distribution was very asymmetrical, right? But when we look at the distribution for the sample mean, we get this nice, smooth, symmetrical curve in a bell shape. Okay, so we've gone from population to sample, but what we really want to do, as we said, is to go from the sample to the population. So probability told us how to go from the population to the sample. Statistics is doing the reverse part. Okay? So, as the sample mean gets very close to the population mean for large samples, we say that the sample mean is a good estimator of the population mean. We can use the sample mean in three different ways. Firstly, as a point estimator for the population mean. Secondly, as the centerval of our interval estimate. This is the confidence interval we showed just now for the population mean. And thirdly, as the basis for our hypothesis test of whether the population mean has a particular value. So in all these cases, we're using our knowledge about how the population relates to the sample to make reverse statements about the population from a particular selected sample. So, sample theory. So, the 95% confidence interval for the population mean, if we use the normal distribution, then the 95% confidence interval for the sample mean is the sample mean plus or minus 1.96 times the standard error. We often approximate that 1.96 by rounding it to 2. Similarly, the 99% confidence interval is the sample mean plus or minus 2.65 times the standard error. So we will explain later on where the 1.96 and 2.65 come from. But again, the key point is in both cases, using the normal distribution approximation, we can draw up a confidence interval without knowing the original distribution of the population. And we can express it in terms of the sample mean and the standard error. So that's very helpful because that allows us to draw statistical conclusions for many situations as long as the sample size is not too small. So, to test hypotheses about the population mean, we use the sample mean as our estimate of the population mean, where we know how reliable an estimate we have by looking at the standard error, because a small standard error means little spread in our estimates, meaning we have a good estimate. So, if our sample is big enough that we can use this normal approximation, then we can find the chance of observing this data or more extreme data if the null hypothesis is true. So to test whether the population mean has a particular value against the two-sided alternative, meaning the population mean does not have that value, which was our first alternative just now when we were looking at the proportion of boys in our school population, then our test statistic, it turns out, is the sample mean minus the hypothesized population mean divided by the standard error. This is something we call the Z statistic, and we can compare this to what we call the standard normal distribution. Standard means mean 0 and standard deviation 1. So we will reject at 5% significance level if this value is outside the range of plus or minus 1.96, and we'll reject at 1% if the value is outside the range plus or minus 2.65. So in other words, for a two-tailed test, we will reject the null hypothesis if the confidence interval does not contain the hypothesized population mean. So that sounds relatively straightforward. The complication, yes, there is still a complication. We need to know the standard error. So the standard error, we said, is the population standard deviation divided by the square root of the sample size. Clearly we know the sample size, but do we know the population standard deviation? Well, quite often we don't know this, so we may need to estimate this as well using the sample. So we can estimate the population standard deviation using the sample standard deviation. So in order for this estimate to be good, again, the sample size needs to be at least 30. Otherwise, we'll need to account for this extra variability using something called the student's t-distribution instead of the normal distribution. We'll come back and look at this later. So, for example, if we come back to our coin tossing and the thing we are measuring is the proportion of heads, then the sample mean is the sample proportion of heads. The standard error is the population standard error divided by the square root of the sample size. So it turns out in this special case of a proportion, we know what the population standard deviation is in terms of the population mean. So the population standard deviation, it turns out, is the square root of p times 1 minus p, where p is the proportion of heads. So the standard error is the square root of p times 1 minus p over n. And in fact, that gives us an upper bound on the standard error, because if you look at p times 1 minus p, its maximum possible value is a quarter. So the standard error will never exceed 1 over the square root of 4 times the sample size. Right? So actually, for the special case of dealing with proportions, we have a limit on the standard error. Of course, if we don't know p, we can use this, right? So we can use this in general. If the sample size is large, we can even substitute the sample proportion in our formula for the standard error. And of course, if we're doing hypothesis testing, we are assuming that we know the value of p, so we can actually substitute that in the standard error. If we only have small samples, then we can go back and use the binomial distribution that we talked about in the previous chapter. Because actually, this is all based on a binomial distribution if we're dealing with proportions. But that makes it much more complicated. So as long as the sample size is not too small, we often use the normal approximation because it's easy to use and it's good enough in practice. So the normal approximation to the binomial gives us that the approximate 95% confidence interval will be the sample proportion plus or minus 1 over the square root of the sample size. And the 99% confidence interval will be the sample proportion plus or minus 1.32 divided by the square root of the sample size. So actually, that means we can do an approximate 95% confidence interval often in our head when we're dealing with proportions. So if you think about it, if the sample size is 100, the square root of 100 is 10, so it's plus or minus 10%. So the sample proportion plus or minus 10% is the approximate 95% confidence interval, right, in a situation where we're looking at proportions. So if you were dealing with a little survey and you asked a yes-no question, right, do you agree with this or not? So we're just, for simplicity for the moment, consider it to be a yes-no question. And if it turned out that we know the proportion of people who said yes, we could immediately test hypotheses about that proportion, knowing that the approximate 95% confidence interval will be plus or minus 10%. So that's actually quite wide, right? Plus or minus 10%. So let's think about it. If we increase the sample size to 400, then that would mean that the sampling error would go down by a factor of 2. It would become plus or minus 5%. If we want to get it down further, we would need to increase the sample size by 4 again, which would mean going from 400 to 1,600, right? So that would go from 5% to 2.5%. So to go down to 1%, we would need a sample size of over 3,000. So you can see then why many surveys have a sample size of only 500 to 1,000, because that already gives us a 95% confidence interval that's no wider than plus or minus 5%. And remember, the cost will generally go up with the sample size. As we said before, the non-sampling error generally doesn't decrease with the sample size, may even go up. So unless you're very confident the non-sampling error is very small, there is often not much benefit in having sample sizes much bigger than 1,000 in a sample, because in a survey sample there are many possible non-sampling errors. Of course, if you're doing a sample in your laboratory, it may be very different, because A, the sampling error may be very small, and B, the non-sampling error may also be very small. Okay, so let's just think a little bit more about the hypothesis test. So when we're doing a hypothesis test, there are two types of mistake. So remember, we talked about mistakes when we were talking about the drug testing using Bayes' law in an earlier chapter. We talked then about false positive and false negative. So we have a similar situation with a hypothesis test. So in a hypothesis test, we have a situation where we could make the mistake of rejecting the null when it's true. This is what we call a type 1 error. So we actually know the chance of rejecting the null when it's true, because that is the significance level we use to reject the null hypothesis. So if we reject at a significance level of 1%, that means we have a 1% chance of rejecting the null hypothesis that's really true. In other words, we have a 1% chance of a type 1 error. So in hypothesis testing, that's the relatively straightforward part, because we have some idea about how large is the chance of making a type 1 error. But that's only one of the types of mistake we can make. The other type of error is to fail to reject the null hypothesis when it's false. This is what we call a type 2 error. This is harder to work out in general because it depends on the alternative, and in our case we have an alternative which is often not specific. So if our alternative is that the coin is unfair, that's a very general hypothesis. We don't know how unfair it is. So in other words, if we have an unfair coin, this means that the chance of heads is not a half, but it doesn't tell us what that value of P actually is. So how easy it is to detect an unfair coin depends on two things. How big a sample we take, right? How many tosses? But it also depends on how unfair the coin is. So let's consider the most extreme case. The most extreme case is a two-headed coin or a two-tailed coin. If we have a two-headed coin, the sample proportion must be 1. So how big a sample do we need to reject a fair coin? So it turns out we need 8 tosses to reject the fair coin hypothesis at a significance level of 1% using a two-tailed test. So where do I get that from? So if we have 8 tosses, the chance of getting all heads is 1 over 256, which is 1 over 2 to the power of 8. The chance of getting all tails is similarly 1 over 256. So a two-tailed test, all heads are all tails, we have a chance of 2 over 256, that's 1 over 128. That's about 0.8%, which is less than 1%. 7 tosses, it's not enough. 7 tosses, we would fail to reject at 1%. So we know that actually 8 tosses are sufficient, right, for us to be able to reject the two-headed coin if we do our test. Now, of course, if I look at a two-headed coin, I know for sure that it's unfair, but we're assuming all we know is the outcome in terms of how many heads or tails we get. But of course, If that coin is not so unfair, we will need more tosses. So 8 is the minimum number of tosses to reject at 1%. But obviously, if that coin is nearly fair, we might need a very large sample in order to be able to reject the hypothesis of a fair coin. Okay? So I'm now going to show you again a simulation to verify the effect. So I'm going to illustrate the effect of changing both how fair the coin is and how big the sample is. So we're going to look at a number of simulations. We'll do simulations from a sample size of 1 all the way up to a sample of 200. So we know a sample of 1 cannot be enough, right? We know the minimum possible is 8, right? 8 is the minimum possible sample size to be able to reject at 1%. And we're going to also look at different levels of unfairness of the coin. So I'm going to look at probability of head running from 0.1 up to 0.5. And then for each of our samples, we're going to show what the sample proportion is and the 99% confidence interval if the coin is fair. So clearly we will reject the null hypothesis if our sample proportion is outside the 99% confidence interval. Okay, so let's have a look at this graph. So this graph is going to show us how able were we to detect unfair coins when we drew one sample of each of these 200 sizes, and we're going to look at 5 different levels of fairness or unfairness in the coins. So if you look at this graph, the red circles are the most unfair coins I'm going to consider. These only have a 10% chance of heads, right? The green pluses are 20% chance. The blue diamonds are 30%. The brown X's are 40%. And the turquoise triangles are 50%. And then the two curves, the bottom purple curve is the cutoff of my 99% interval at the bottom limit, and the yellow curve at the top is the upper cutoff limit for my 99% confidence interval. So you'll see that for very small sample sizes, I cannot reject because the curve is outside the limits of 0 and 1. So remember we said we need a sample of at least 8 minimum to be able to ever detect and reject the fair hypothesis. So let's have a look to see what our results look like. So let's look at, first of all, the red circles. So this is the very unfair coin. So if you look at this, the question is, are the red circles outside the 99% curve limits? And you will see, if you look very carefully, it's a little bit hard to see in this video, but if you look at your course book, you will see that by the time we've got to a sample of about 15 perhaps, there are no more red circles inside the confidence limits. Right, so we're pretty sure that a sample of 15 is sufficient to reject the null hypothesis, the fair coin, if we have coins which only have a 10% chance of heads. We don't need too big a sample. Okay? So let's look at next at the 20%. So this is the green pluses. So if you look at the green pluses, you can see that by the time we got to 30, the green pluses are all outside the curve. Right? So we need a somewhat bigger sample if our coin is not quite so unfair. Okay, so now let's look at the blue diamonds. So if you look at the blue diamonds, you will see there are blue diamonds beyond 50, I think, to about 70 or 80. We still have some blue diamonds inside the interval. But by the time we've got to around 100, all the blue diamonds from there on are outside the curve. So a sample of 100 roughly should be sufficient to be quite confident that we can detect a 30% coin. Okay, so what about the brown X's? So if you look at the brown X's, there are brown X's inside the curve pretty much nearly all the way up to 200. So even a sample size of 200 is barely enough to detect a coin with a 40% chance of success as being unfair. Right? So the sample size needs to become quite large if we have a coin which is only slightly unfair. In fact, if you ever tried making an unfair coin, it's quite hard to make a coin that is unfair, even to that degree of unfairness. Unless, of course, it's a two-headed or two-tailed coin. Okay, so that's the unfair coins, but what about the fair coin? So the fair coin, right, remember, is our turquoise triangles. So if you look at the turquoise triangles, you can see there are one or two turquoise triangles outside the curve. There's one, I think, which is clearly outside the curve. And if you look at the bottom limit, I think if you look carefully, you'll find another one or two which are outside the curve. So overall, we have about 2 cases out of our 200 experiments where we would have rejected the null hypothesis even though it's true. And in fact, that's actually what we expect, because we set the significance level at 1%. So 1%, and then we do this experiment 200 times, we'd expect on average that on 2 of those 200 experiments, we would have rejected the null hypothesis even though the coin is fair. Right? So it may be a little bit more, or it may be less, but on average we would expect to make the wrong decision in that direction, right? So that's the type 1 error, about 2 times out of 200 if we set the significance level at 1%. If we'd set the significance level at 5%, we would have expected to make that wrong decision 10 times, not just 2 times. Right, so how we set the significance level relates to the risk of making a type 1 error, but the type 2 errors we've seen, we need to not only know the sample size, but we also need to know how far away we are from the null hypothesis. Okay, so that means the related question is, how likely are we to reject the null when it's false? This is called the power of our test, the statistical power of our test, and is simply 1 minus the chance of a type 2 error. So this depends on what the true population mean is, but doing this calculation for assumed true population mean allows us to check whether our sample is likely to be useful or not. Because if our sample size will not likely allow us to reject the null, even when the true value is quite different, then our sample is of little use. So if you're seeking funding for a piece of research where the cost of doing the research is high, it's likely that the funding agency would expect you to be able to show that your sample size is such that the chance of being able to reject the null is reasonable. In other words, that the power is sufficient. So usually it would be expected that the power should be at least 80%. Given possible likely values of the population mean and variance, how would you know those? Well, you might have done a pilot study, or perhaps based on the literature review or a theoretical argument. And conversely, if the power is very high, if the power was, say, 99%, they might even question whether your sample size is bigger than it needs to be. Okay? So, remember, in our coin example, we can choose a sample size that is likely to reject if we have some idea of how biased our coin might be. So in this particular case, it's not too hard to calculate the power. There are web pages, for example, on the internet. There is free software called G-Power. In more complex situations, it may be quite hard to have a theoretical calculation, but then we can always do a simulation similar to the one I showed you just now. As long as we do a big enough simulation, we should be able to get a quite accurate estimate for the power of our test. Okay, so we've sort of been waving our hands around rather in terms of the formulae. So we need to introduce rather more carefully what the statistical formulas are for both our confidence intervals and for our hypothesis test. Now, as I mentioned, in general, we may not know the population variance, so we may not be able to do the confidence intervals or hypotheses test directly. But as I said, for large sample sizes, we may be able to use the sample variance as a replacement, whereas for smaller sample sizes, we need to replace the bell-shaped curve coefficients with ones using a student's t-distribution. So the student's t-distribution allows for the fact that we're using the sample variance instead of the population variance, recognizing that our statements won't be quite so precise. So the confidence interval will be wider if we use the student's t-distribution, accounting for the extra variability due to using the sample variance. So, first of all, if we start with the normal distribution, for large samples, then the 95% confidence interval is the sample mean plus or minus 1.96 times the standard error, as I explained, where the standard error is the population standard deviation over the square root of the sample size. Now, where does this 1.96 come from? This is called the Z value. To be more precise, we use the notation Z 0.025 because it is the value such that there is a 2.5% chance of getting a bigger value for a standard normal distribution. So remember, the other 2.5% is the chance of a value below minus Z. So overall, that means there is a 95% chance of getting a value inside the interval from minus 1.96 to plus 1.96, and a 5% chance of getting a value outside that interval. Similarly, for a 99% confidence interval, we use 2.65, which is Z 0.005. We can get these values from statistical tables or a calculator, meaning Z 0.005 means there's a 0.5% chance of getting a value bigger than this, another 0.5% chance of getting a value less than minus this. So again, 99% chance of a value inside the interval and a 1% chance of getting a value outside the interval. So these Z values are what we call the quantiles for the standardized normal distribution. Quantile meaning it relates to the chance of getting a value greater than this. And standardized means a normal distribution with zero mean and unit variance. So the way the formula works is that the sample mean approximately follows a normal distribution with mean equal to population mean and with variance equal to population variance divided by the sample size. Equivalently, we're saying the sample mean minus the population mean over the standard error follows a standard normal distribution with mean 0 and variance 1. So that's why 95% of the time it will be between plus or minus 1.96 and 5% of the time it will be outside that range. Or alternatively, we're saying the sample mean is between the population mean plus or minus 1.96 times the standard error, and that's where we got our confidence interval formula for. And again, as I said, hypothesis testing, we're essentially doing the opposite. Instead of asking what are the likely values for the population mean, we're asking whether the hypothesized value for the population mean is reasonable. In other words, does it lie inside or outside the confidence interval? If it does not lie inside the interval, we would reject the null hypothesis at a significance level of 100 minus the coverage of the confidence interval. So if it's a 95% confidence interval and we get a value outside, then we reject it at a significance level of 5%. So equivalent way of expressing the hypothesis test is that we reject the null at 5% if the sample mean minus the hypothesized population mean divided by the standard error is outside the range of plus or minus 1.96. Now, this is, of course, using the two-sided hypothesis test relating to the two-sided confidence interval. But what if we want to do a one-sided test or a one-tailed test? So, for example, we were considering a situation where the bias in gender was towards either boys or girls, or the bias in our coin was towards heads or tails. But what if we're only interested in bias in one direction? So, for example, if we have good reason to believe that the coin might only be biased towards heads, why might that be? Well, perhaps I'm gambling with you and you're betting on heads. So the only reason you might bet on heads would be if you thought the coin was biased towards heads. So that's my concern, is whether the coin has been biased in that one direction. So for the one-sided test or the one-sided confidence interval, then we're only interested in a confidence interval that covers values up to a particular value or down to a particular value. So the 95% confidence interval would relate to the Z 5% cutoff, not the Z 2.5% cutoff. So the Z 5% cutoff is 1.645. So our 95% confidence interval would cover all values up to the sample mean plus 1.645 times the standard error, or in the other direction, all values down to the sample mean minus 1.645 times the standard error. So again, if this interval does not include the hypothesized value, we would reject at 5% using a one-sided test. Now, of course, that means it's easier to reject the null hypothesis if our value is already on that side. So it's tempting then to say, oh, I'm only interested in this particular situation, so I'm only going to do a one-sided test, right? So the decision to choose one-sided test must be before we do the testing, not after looking at the results. Otherwise, that's cheating, right? You're essentially making it easier to reject. Now, historically, people would work out where the cutoff values are, but these days, using statistical packages, what they actually normally do is calculate what's called the observed significance level, which means the probability of rejecting the null incorrectly for this particular value of the test statistic. So this way we don't need to use statistical tables, but simply decide whether this observed significance level is sufficiently small for us to reject the null hypothesis. Meaning, if our cutoff is 5% and we get an observed significance level that's less than 5%, we know we'll reject at 5%. If we get an observed significance level of 0.1%, then we know we would reject at either 5% or 1%. Now, the other thing I mentioned was if the population variance is unknown, then we needed to use the student's t-test. So when the population variance is not known and we've estimated the population variance from the sample variance, we replace the Z value by a t value which will be slightly larger and takes into account the fact that we have less information because we don't know the population variance. So this t value is a little bit more complicated because it also depends on the sample size, because the sample size affects the accuracy of the variance estimate. So this we use something called the degrees of freedom, which is the sample size minus 1. So if the sample size is at least 30, the t-value in practice is very similar to the z value because there is not much extra uncertainty from estimating the variance. So if the standard error is estimated because the population variance is not known, then the formula is just simply now the sample mean minus the population mean divided by the estimated standard error is a t-distribution with n minus 1 degrees of freedom, where n is the sample size. So instead of getting plus or minus 1.96, we'll get slightly larger numbers and hence a wider interval than when using the z value, unless the sample size is so large that the t value and z values are essentially the same. Now, I've moved back and forth between sample means and sample proportions because the theory is essentially the same, right? We can talk about sample proportions as our estimate for the population proportions. As I said, if we are doing hypothesis test, we know what p is, and hence we know the population variance. Or we can use that conservative limit that p times 1 minus p can never exceed a quarter. If we have a small sample, we can use the exact tables for the binomial distribution to find the confidence interval and do the hypothesis test instead of using the normal approximation. So let's have a look at an example. We're going to look at a sample of the heights of 63 children who are 12 years old, and we're going to show what the 95% confidence interval is, and we're going to test all three alternatives against a null hypothesis that the mean population height is 60. So this is an American data set, so they still work in the dark ages of feet and inches. So this 60 means 60 inches or 5 feet. So let's have a look. So what we have here is the output from JMP. On the left-hand side, we have our graphical and numerical summaries. On the right-hand side, we have our confidence interval and our t-test. So first of all, let's look at the histogram and the box plot. You can see that actually the distribution histogram goes from roughly 55 to 65. But of course, the sample mean is somewhere in the middle of that. And you can see the box plot that the interquartile range runs from roughly 57 to 62. And you can see the median is around 60. The quantiles show us in particular that the minimum is 50.5, the maximum is 66.3, and it shows us exactly that the median is 59.5. It shows that the quartiles are actually 57.3 and 61. And then we have our summary statistics. The mean is actually 59.18. The standard deviation based on the sample is about 3. So the standard error is the standard deviation divided by the square root of the sample size. The sample size is 63. The square root of the sample size is then about 8. So 3 divided by 8 is roughly 0.38, which is the standard error of the mean. So we can already roughly work out the 95% confidence interval in our heads. Plus or minus 2 standard errors is about plus or minus 0.76. So hence we've got already on the left-hand side, the 95% confidence interval goes from 58.4 up to 59.9. So you'll notice that 60 is not inside the 95% confidence interval, but it's only just outside. So we can already guess that the observed significance level will be just a little bit less than 5%. So now we come to the right-hand side. It has two confidence intervals for both the mean and the standard deviation. In this case, we're not really interested in the confidence interval for the standard deviation, but you can see it goes from roughly 2.6 to 3.7. So we know the standard deviation quite accurately. There's not too much variability left. Our sample size is big enough, meaning that our t results are not too similar to the z results. So the confidence interval for the mean we've already seen. It goes from 58.42 up to 59.94. Now we come to the hypothesis test. So we've hypothesized that the value should be 60. Our sample estimate is 59.18. The degrees of freedom, I said, is 1 taken away from the sample size, so it's 62. So the standard deviation, we said, is about 3. So the test statistic, remember, the t-statistic will then be the difference between the hypothesized value and the actual estimate divided by the standard error. So 60 minus 59.18 is about minus 0.8. The standard error, we said, is about 0.38. So the test statistic is minus 2.15. Minus 2.15, we would reject this if we were using a z-test because that's outside the range of plus or minus 1.96. So what about our significance levels? So it gives us 3 different outcomes, observed significance levels. This corresponds to our 3 different alternative hypotheses. So we need to understand a little bit about how JMP summarized this. So the first one says probability greater than vertical bar t vertical bar. So the vertical bars, you should remember in mathematical notation, means absolute value. So this is JMP's shorthand for saying when we don't care which tail it's in, is it a positive or a negative value, the two-tailed test, this is telling us the observed significance level, it's 3.6%. So as I said, we could already see that because it's outside the 95% confidence interval, the observed significance level must be less than 5%, so it's about 3.6%. Then we have the 2 one-tailed tests. So let's have a look at the graph underneath because this shows us very nicely what's going on. So the red vertical line is showing us the value we actually got, right? The 59.18. The hypothesized value, of course, is the center of our distribution, 60. And so the 95% confidence interval is based on the blue areas on the left and the right. Okay? So you'll see we're just into the dark blue area, meaning we would reject at 5% if we were doing the two-tailed test. Now, of course, that means that if we're saying probability of getting a value bigger than this, that becomes 1 minus the area to the left of the red vertical line. So that's about 98%, right? Because that 3.6%, we've got 1.8% to the left, 1.8% to the right. So if we're only looking at bigger than these values, 98% observed significance level, less than this is about 1.8%. So actually, when it comes to height, often we're really only interested in whether the children are below normal height. Because generally, if you're below normal height, that means that you haven't had sufficient nutrition, right? You haven't been able to grow properly. So quite often we are actually only interested in whether children are below normal height. We often might use the one-tailed test to the left. So this says actually observed significance level for that one-tailed test is about 1.8%. So we have reasonably good evidence that these children on average are below the average height of 60. Right, so there's some evidence. It's not compelling evidence, right? The observed significance level is 1.8%. Now, we need to recognize the problem of multiple tests. We sort of dealt with this just now. If we go back to the page where we were doing the multiple tests, right? Remember this, where we're doing the multiple tests. And I said that we ended up with about 2 or 3 times when we had rejected the null hypothesis incorrectly. So we had here done 200 tests. So with 200 tests, it's quite likely that by chance we will, at least on one occasion, if not 2, reject the null hypothesis even though it's true. So we need to take into account if we're doing many tests. So how do we do that? So this is what sometimes is known as p-hacking if you do not make an adjustment when you do many tests. Right? So the chance of making one false rejection increases proportional to the number of tests you do. So this can be adjusted for using something called the Bonferroni Correction. The Bonferroni Correction says that the effective significance level is the stated significance level multiplied by the number of hypotheses you tested. So my original example of the coin tossing, right, I tossed the coin I did 200 experiments, and each one I set the observed significance level to 1%. So 200 times 1% is 200%. In other words, I have no real evidence of there being unfair coins if I take into account that I was doing 200 tests, not just one. So the fact that I got one or two where I rejected with my fair coin isn't surprising. Okay? Now, there is a slight problem with using the Bonferroni correction, and that is that it's then very hard to detect effects when you do a large number of tests, meaning the power is low, so we're unlikely to detect that the null hypothesis is false. So Bonferroni is if we're saying we don't ever want to falsely reject the null hypothesis. Right? But what if instead we are concerned about the discovery rate, what we call the false discovery rate, meaning the proportion of discoveries which are false, where discovery means we reject the null hypothesis. So in this case, we care about the proportion of false rejections rather than the number of false rejections. So if that is what we're focused on, so this would be the sort of situation such as doing genetic testing. So there is an alternative approach to Bonferroni called the Benjamini Hochberg procedure. So this procedure controls the false discovery rate at level alpha, where alpha is our probability of rejection. So the way it works is that if we've tested m different null hypotheses, we list the p-values, the observed significant levels for those m null hypotheses in ascending order, and denote them by p1 to pm. And we find the largest k such that pk is less than k times alpha over m. And so then we will reject the null hypotheses for discoveries 1 to k on the basis that we think those particular null hypotheses probably are false, right? Where we're controlling the risk. Here we're controlling the risk of a false discovery. Okay, so geometrically this corresponds to plotting p of k versus k over m, drawing the line through the origin and declaring discoveries for all the points below the last point below the line. So if the m tests are independent, then this is okay. In some forms of dependence, it's still okay. So I'm going to show you now a simple example where we did 9 tests and we'd set our alpha value, our significance level, at 5%. So Bonferroni would suggest that we need to divide the p-values by 9 in order to account for this. So divide the p-values by 9 would mean we would need to only reject if the p-value was below 0.55%. Whereas Benjamini Hochberg says, look at the line with slope 5% and reject all tests until there's one above the line. So let's have a look at this. So you can see here, so the red values are the original p-values. If we're dealing with the false discovery rate, then we get the blue values. Okay? So you will see we have sorted the p-values in increasing order. And we said if we want to control the risk of a false discovery rate of 5%, then we draw that red diagonal line from 0, 0 up to 1.5. And then we reject the hypotheses which are below the red diagonal line up to that point. So the first three are all below. We reject those. The ones other than that are above. So you'll notice if we did no correction, we would actually reject the first four hypotheses. So the fourth one you will see is quite close to 5%. But if we take into account that we were doing 9 tests, then clearly the true significance level for the fourth one is well above 5%. Okay? So this is an alternative approach where our focus is on the false discovery rate, the proportion of false discoveries, rather than saying we want the risk of making any false discoveries to be controlled at 5%. Okay, so we now have done confidence intervals and hypothesis testing for population means and population proportions. How do we extend these ideas to other situations? So the most common extension is where we want to test for a change in the population mean. In other words, is the mean of population 1 the same as the mean of population 2? So obviously the null hypothesis is that the difference between the population means is 0. Now, within this we have two different situations. Whether we're measuring two different populations of individuals, and hence two quite distinct samples, or whether we're measuring the same sample twice. If we're measuring the same individuals twice, then actually it's much more sensitive to look at the change in measurements on those same individuals. So for example, if I wanted to know whether my course is changing your knowledge, I test your knowledge before the course and I test it after. If I look at the change in your score, that's a much more sensitive way of assessing whether my course made a difference than if I just look at the average scores before and after. That's because by looking at change within individuals, we can exclude the variability across individuals and focus on the variability within. Okay? So let's have a look at an example. Let's say we had 64 individuals with an average score of 50 and a standard deviation of 8. If we improve the score of half the individuals by 1 and half by 2, we now have a new average score of 51.5. If we match the individuals and look at the change, we have 64 differences with an average change of 1.5 and a standard deviation of 0.5. So if we calculate the 99% confidence interval for this mean change, it turns out to be roughly 1.3 to 1.7. So we're quite certain that there is a positive change, even if it's not big enough to be useful. So this is what we call a paired t-test. Paired because we're matching the individuals before and after. T-test because in this particular situation, actually, we don't know the variability in general of the change. We have to assess that based on the sample, right? The theoretical argument can't tell us. The theoretical argument told us that even if we know the variability of the individuals before and after, that doesn't tell us about the variability of the change in those individuals. So we have to estimate the variability of the change from the sample. So by looking at the differences for each individual, we're just treating the change in score as our variable, and we're applying exactly the same statistical procedures to the changes to get confidence intervals and hypothesis tests for the difference in the population means. As I said, it's paired because we're looking at matched individuals. It's a t-test because we do not know the population standard deviation for change. Okay, let's look at a second example. This one we're going to look at the output from the statistical package. This is 24 measurements of the temperature inside and outside of a box at different points on the box. So we're going to create a new variable called diff, which is the difference between the inside and outside temperature at those 24 points on the box. And we're going to show the confidence interval and the test. So again, on the left, we have our graphical and numerical summaries. So first of all, you can see that the distribution goes from roughly -3 to +3. There's quite a lot of variability. But the box plot shows us that most of the data is, half the data at least, is in the range of roughly -1.3 to roughly 0. But we have some differences all the way up to +3. Okay, so our summary statistics, the median is -0.4, the mean is -0.43, the standard deviation is about 1.28. Our sample size is only 24, so the square root of the sample size is roughly 5. So the standard error is about 0.26. So our 95% confidence interval goes from roughly -1 to +0.1. So the right-hand side is indeed showing us that confidence interval. And again, we have our 3 hypothesis tests. These are all based on a t-test. The hypothesized difference, we said, of course, is 0. The sample estimate of the difference is -0.43. The standard deviation, we said, is 1.28. The standard error, we said, is 0.26. So our test statistic is going to be -0.43 divided by 0.26, which is about -1.66. Clearly, that's not going to be significant. So in our two-tail test, at least, the observed significance level is about 11%. So that's, again, the areas under the curve in the graph underneath. If we look at the below part, you will see even that is still 5.5%, which is half of the 11%. So even if we were doing a one-tail test where we're testing whether we get a negative value, we would still not be able to reject this hypothesis at 5%. Okay? So this is relatively straightforward. It's essentially the same as we were doing in the t-test before, but we're just looking at the change variable rather than the original measurements. So now we come to the two-sample t-test. So two-sample t-test means we either have different populations or at least we have different samples. What then? So again, the difference in sample means is clearly going to be the best estimator of the difference in the population means. Where it's more complicated is the standard error of the difference. So the standard error of the difference in this case will be essentially based on the variability of the difference in the two sample means. So the variability of the first sample mean is just the square root of the population variance 1 over sample size 1. The variability in the second sample mean is the square root of population variance 2 over sample size 2. But the key point here is we have to recognize is that when we're looking at the difference in the two sample means, the variances add, they do not subtract. And in fact, they add on the variance scale, not the standard deviation scale. So that's why the standard error of the difference, we need to add the variability of the two sample means before taking the square root to turn it back into a standard error. Okay, so this is quite different, and this is why it's called a two-sample t-test, because again, we may not always know what the variance is for the two populations. If we do, then in theory, we would not have to use a t-test. We could use a z-test if we actually knew what the population variances were for the two populations, but in many cases we don't. Now, when you look at people reporting two-sample t-tests, they often talk about a pooled two-sample t-test. So what does pooled mean? So let me give you a little story to illustrate the idea of pooling. So before the virus hit, my wife and I occasionally like to go out and have sushi. And so the restaurant where we like to go and have sushi has a belt, a rotating belt that goes around the restaurant containing little plates of sushi. And as I'm sure most of you know, you pick the plates off the tray, and after you've eaten the sushi, you pile up all the plates. And at the end of the meal, the waitress comes and counts how many plates you have of different colors in order to work out how much your bill should be. Right? So the ones with gold are the very expensive ones. The plain color ones are relatively cheap. And that's relatively easy then to work out how much to charge you. Now the thing about sitting next to the belt is you're sitting quite close to other people. So again, I don't know how they're going to handle this in future. It's going to be difficult, right? Because of social distancing. But anyway, before the virus, you'll be sitting quite close to other people, so you can't help but overhear their conversations. So when my wife and I were sitting down, there were two young ladies sat down next to us. And they said something to the waitress when they sat down, and it wasn't quite clear to us what they said. So they were taking plates off the belt, and that's straightforward. But the thing about that restaurant is if you want something that's not coming around on the belt, let's say you want a nice expensive piece of tuna, you can order that and they will bring it out to you directly from the kitchen rather than you needing to wait for it to turn up on the belt. So these two young ladies ordered several dishes from the kitchen. Okay, what's the problem? Well, the problem is that the issue that how you handle those extra dishes. You can't tell by the color of the plate how much they charge. So those ones are marked down separately. They keep a separate record of the dishes you've ordered directly from the kitchen. So how did this become a problem? Well, when it came to the end of the meal, the young ladies asked for the bill. And so the waitress wrote out a bill for them, and they said, no, no, no. When we came in, we said we wanted separate bills. We did not want a combined bill. And then this caused a problem. Usually you just look at, okay, so if you want separate bills, these are your plates, these are my plates. And we can look at the colors. But it wasn't clear who had eaten the dishes that came out from the kitchen. So then the waitress got into an argument. So I think in the end they had to agree, the two young ladies had to work out amongst themselves who had which plates, and then essentially agree to split the bill in some appropriate manner. So they were very angry because what they actually wanted was a pooled bill. They wanted to combine the bills for the two of them and then just split it at the end, presumably equally. Right? So the similar issue is here. We're assuming that way of splitting a bill assumes that maybe you ate a little bit more than me this time, but maybe another time I'll eat a little bit more than you. So we assume on average this is fair, and we assume that the variability is similar. So in a pooled two-sample t-test, you're assuming that the variance is the same in the two populations. So why would you want to make that assumption? Well, because if you're doing the t-test calculation by hand, it is much easier to do the calculation if you can assume the variances are the same in the two populations. Right? But these days, we generally aren't doing the calculations by hand. A computer is doing it for us. So, but people have got into the habit of doing a pooled two-sample t-test. The problem with doing a pooled two-sample t-test is actually you first of all need to check, are the variances the same? So you need to do something called Levene's test to first check whether the variance is equal, and then you can do if you don't reject that hypothesis, then you can combine the variances. So it becomes a two-stage process which has no real benefit whatsoever. So instead, you should really be using Welch's two-sample t-test, which does not assume equal variances. So it's more complicated because it turns out the degrees of freedom calculation is not simple. But that's handled by the statistical package automatically, so you don't need to worry about it. Right? So generally, when you're doing a two-sample t-test, I would not recommend using the pooled test. Generally, you should use Welch's two-sample t-test instead of doing this two-stage procedure. So, for a large sample, the 95% confidence interval for the difference in means is, of course, still the sample mean 1 minus sample mean 2 plus or minus 1.96 times the standard error. The only complication is that the standard error is more complicated, but in general, you're not going to do these calculations. This is going to be done for you by the statistical package. So in the example I gave you up above, if I actually didn't have the same individuals measured twice and I couldn't match them, the problem would be that the standard error would be root 2. So my 95% confidence interval would be 1.5 plus or minus 1.96 times the square root of 2, which clearly includes 0. So I would fail to reject the null. So in other words, if I was not matching my individuals before and after, it's not very likely that I would be able to detect that there had been a change of about 1 or 2 units in your scores after my exam. Now, we need to be very careful here because there is also a validity issue. So when I said I could use the test, if I come back to the previous one, the one where we were looking at the paired t-test, and I said I was looking to see whether the change was different from 0. So I'm implicitly assuming that I know what is the cause of that change. Right? So if I measure your performance before and after my course, I'm assuming that if you've improved, it's because I was a good teacher. But that may not be the case. It might be that you didn't bother to look at the teaching materials and went off the library and read a book. You decided that the teaching materials were no good and you found your own teaching materials, and that's why you did so well. So in that situation, my conclusion that I know the cause of the change would be faulty. Right, so this comes back to our earlier discussion about the validity of our research design. So often in these situations, you actually would have a control group. In other words, you might have another group of students that you measured at the same 2 time points to see whether their scores improved in a similar way or changed in a similar way to the ones who came to my course. So the real question would be, for example, I might compare my teaching to self-study and say, is my teaching any better than just telling the students, go and read a book in the library? Then at least that would be a fairer comparison as to whether my teaching actually made a difference. The other issue is, of course, if this is a score on a scale of 0 to 100, if the difference is only 1.5, you could argue that that difference is not meaningful. It's not a significant change. So we need to be very careful. People talk about statistical significance. That does not mean that the difference is big enough to be meaningful in a scientific sense. It just means it's big enough that we could detect that it wasn't due to chance. So statistical significance is a very different issue from scientific significance. We need to be very clear about that. Okay, so let's have a look at an example of the 2-sample t-test. This time we're going to look again at the heights of 63 children, but this time we're comparing the boys and the girls. So the question is, are the boys and the girls different in height? So we're going to look at this in a pooled situation and a non-pooled situation. In other words, we'll look both with the assumption of equal variance and without the assumption of equal variance. So you'll see the first half of the page is where JMP has written assuming equal variances, the t-test of male minus female. So the difference in heights is minus 0.6, meaning the girls actually are slightly taller than the boys at this age. The standard error of the difference is 0.765. So you can see the t ratio is minus 0.8. So clearly this is not going to be significant. It's nowhere close to plus or minus 2. So the 2 sample t-test, right, you'll see the observed significance level is 41%. The confidence interval goes from minus 2.15 up to plus 0.9. So again, the graph on the right shows you what's going on. We're testing the hypothesis of 0 mean, and you can see that our result is not that different from 0. So it's quite possible and plausible that our result is just due to chance and that there is actually no difference between the heights of the boys and girls at this age. Okay? And then the second half of the page is exactly the same, except this one does not assume the variance is equal. So the top half is a pooled 2 sample t-test. The second half is an unpooled 2 sample t-test. And you will see in this particular case the results are almost identical. There is basically no real difference. You'll see that the degrees of freedom is rather odd. The degrees of freedom is, instead of 61, we get 60.7. This is the adjustment that takes into account that the variabilities are not quite the same in the males and the females. But it's so similar that we get almost the same result, because of course the difference is the same. It's still minus 0.625, just that the standard error and the degrees of freedom are slightly different. Now, I want to introduce one more concept here before we move on. This is what's called effect size. So the standardized effect size is a standardized measure of the strength of a relationship. In this case, it is just a standardized mean difference between the two groups, right? So if we're comparing two groups, the effect size is saying how different are those two groups. So this is important if we're trying to calculate the power for a 2 sample case with different sample sizes for an assumed effect size. So the effect size for a 2 sample t-test is the difference in the population means divided by the standard deviation. So you'll notice this has no units because the population mean and the standard deviation are both in the same units, and it does not depend on the sample size. So that's basically saying a random individual from population 1 compared to a random individual from population 2, how different are they on average relative to the variability within individuals in the population. So this is basically telling us how difficult it's going to be to detect a difference. Right? So if the effect size is large, we will not need a very big sample. If the effect size is small, we're going to need a big sample to be able to detect a difference. Okay? So effect size is a more general concept, which is often used in power calculations. I'm just showing it you for this situation because it's relatively simple and straightforward in this case of a 2 sample t-test. Okay, so we've looked at how to do hypothesis test for population mean, for population standard deviation, for the difference in 2 populations where it's the same or different individuals. What's another situation where we can do hypothesis test? So now we're going to talk about categorical data with more than 2 categories. So we've already dealt with categorical data with 2 categories. That was our male-female or head-tail situations. But what if we have more than 2 categories? How would we do hypothesis tests? So with 2 categories, we could just use the binomial distribution, and we knew if the samples are big, we can use the approximation from normal. But what if we have more than 2 categories? How can we test hypotheses in this situation? So we need to introduce a different concept called goodness of fit. Now, goodness of fit actually is a very bad name for this concept. It really should be called badness of fit, because our goodness of fit criteria will be 0 if we have perfect fit, and will be large if we have a bad fit. So the way we're going to introduce this concept, we can apply it in all situations where we have count data and where the alternative hypothesis is two-tailed and we have 2 or more categories, right? So for 3 categories, for example, the null hypothesis would simply be that we know the proportions of the 3 categories. Could be that they're equal, or could be something else, but we must have specified the 3 proportions, and the alternative would be that at least one of the proportions is different from what we've hypothesized, but we don't know how it is different, right? So it can only let us know whether the specific proportions are reasonable compared to the alternative. We can't use a specific alternative in this case. So for example, very simple case, if we have data for how many people in our sample live on Hong Kong Island, Kowloon or New Territories, and we want to test the hypotheses whether the proportions in our sample match the proportions in the census data. Okay? So that would be a way of checking whether our sample is representative in terms of where the people live. So there's more than one test statistic. The one that's most common we're going to start with is called Pearson's chi-squared goodness of fit statistic. It's sometimes called X squared. So what is Pearson's chi-squared goodness of fit statistic? We're going to look at the squared differences between the observed and expected counts for each of our categories. We're going to add those up, but before we add them up, we're going to scale them by the expected counts for that category. So obviously, if all the observed counts equal the expected counts for all our categories, X squared is 0. But if the observed and expected counts are quite different, then X squared will be relatively large. So observed means the actual count. Expected means the count we would expect if the null hypothesis is true. So we said the null hypothesis must tell us the proportions for each category. If we multiply that by the sample size, that should tell us the expected count for that particular category. And then the sigma here just means we sum up this over all the categories, right? So if k is the number of categories, we will compare our x squared value against the tables for the chi-square distribution with k minus 1 degrees of freedom. It turns out chi-squared means something like adding up squared standard normal variables. So chi-squared with k minus 1 degrees of freedom is the distribution for adding up k minus 1 independent squared standard normal variables. Right, so we're doing something like this. It's something like saying the deviation of the counts, the observed minus the expected count, we're squaring those and adding them up. The only slightly tricky point here is, why are we dividing by the expected count? Well, the reason is because for account data, the variability is proportional to the mean, to the expected value. So in order to compare the data from different categories, in order to scale it, we need to divide it by the expected count for that category as part of our summing up process. Okay? So the calculation of x squared and the probability of observing this value of x squared or a bigger value can be easily found using a computer package. Now notice I said x squared of 0 is consistent with the null hypothesis. In fact, people have sometimes been able to detect cheating in research by checking the x squared value. If the x squared value is too small, that also is a bit suspicious. So there are data sets where people had x squared values of 0. So that means there's a perfect fit of their data to the null hypothesis. So that's a bit suspicious. So, but in this situation where we're testing the null versus the alternative, the issue is simply, is x squared big enough to reject the null hypothesis? So we're going to calculate the probability of observing this value of x squared or a value more extreme. That will be our observed significance level for our hypothesis test, right? So we calculate x squared, then the probability of getting a value, this value or something bigger. And if that probability is sufficiently small, then we believe that our data is inconsistent with the null hypothesis. So there is an approximation in here, but this approximation works reasonably well. The only thing we have to be a little bit careful is that the expected counts are not too small. So we're assuming that the expected count is at least 5 for each category. Otherwise, we need to use a more careful approach, a more complicated approach than this. Now, there is another statistic we can use in this situation that's called the G-squared likelihood ratio statistic, which is essentially just another approximation to the chi-squared statistic. So the G-squared value is calculated as twice the sum of the observed counts times the log ratio of expected over observed counts. So this is a little bit harder to guess, to understand intuitively, but let me try to explain. If all the expected values are equal to the observed values, then expected over observed is 1, log of 1 is 0, and G squared is 0. So G squared will be 0 only if all the expected and observed counts are equal. If they're not equal, then G squared will be bigger. So G squared is another way of assessing how different the expected and observed counts are. Now, one important point here is when we're doing this, we're assuming the data we have are nominal scale, meaning there is no ordering in the categories. If the data is ordinal, then there are more sensitive statistical methods that should be used. So if I ever get a statistical paper for review and the data is ordinal scale, and they use Pearson's or G-squared likelihood ratio statistic, I will normally send it back asking for a revision because there are better statistical methods which are more sensitive in testing the null hypothesis, okay? But we're assuming here that this is nominal scale data. So I want to illustrate to you how well x squared works using simulated data. So this is data I simulated for a course for linguistic students. So this was simulated to cover 3 languages. So it's about the mother tongue of students in an international school. So the simulated data actually has 1/3 have English as the mother tongue, 1/2 have Cantonese as the mother tongue, and 1/6 have Putonghua as the mother tongue. So I'm going to show you some experiments, simulated experiments, with 2 different sample sizes to illustrate how well we're able to detect this set of proportions against the proportions of equal proportions. So equal proportions would of course mean 1/3, 1/3, 1/3 for English, Cantonese and Putonghua. So our null hypothesis is going to be 1/3, 1/3, 1/3. I know in this case the null is false. So am I able to detect that the null is false with sample sizes of 30 and sample sizes of 60? And I'm going to do 1,000 simulations so we get a pretty accurate picture about what the power is of our test in these 2 situations. Okay? So our counts are 18, for example, English, 31 for Cantonese, and 11 for Putonghua, for a sample size of 60. Then under the null hypothesis, the expected values would all be 20. So the x squared value would be, first of all, 18 minus 20 squared over 20 for English, plus 31 minus 20 squared over 20 for Cantonese, plus 11 minus 20 squared over 20 for Putonghua. You add those all up, you get a value of about 10.3. Okay? That's just showing you how the calculation works. You don't need to do it. We're going to get the computer to do the calculations for us. I just want to illustrate how it works. So on the left-hand side here, we've got the results for a sample of 30. On the right-hand side, we have the results for a sample of 60. So if we look up in statistical tables, it turns out that the degrees of freedom, as I said, is the number of categories minus 1. We have 3 categories, so it's 2 degrees of freedom. And the 95% cutoff or 5% cutoff, so 95% confidence interval, 5% significance level, the cutoff value is 5.99. In other words, we will reject the null hypothesis at 5% if we get an x squared value of 6 or above. So let's have a look to see how did we do. So this is showing you the distribution of the x squared values in our 1,000 simulations. So the left-hand side with our sample of 30, the median is about 6, meaning the power is about 50%, because that means about half the time, just over half the time we did this simulation, we got an x squared value such that we would reject the null hypothesis at 50%. Sorry, at 5%. Okay? And you can see from the distribution, indeed, the median is around 6. The right-hand side shows what happens if we increase the sample size to 60. So now you can see the median value of x squared is about 11. So that means it's much more than 50% of the time we will reject the null hypothesis. In fact, the quartile, the lower quartile, is 7.5. So that means that more than 75% of the time we will reject the null hypothesis at 5%. In fact, if we look it up carefully, it's about 85% of our sample we would reject the null hypothesis with a sample of 60. So meaning, with a sample of 30, the power is about 50%. With a sample of 60, the power is about 85%. So this is quite impressive, right? With just a sample of 60 children, even though the difference in the proportions of different mother tongues is not that different between the null and the alternative, remember, we're assuming a third, a third, a third in the null hypothesis, but the actual proportions are a third, a half, a sixth. So we're able to detect that quite reliably with a power of 85% with a sample of 60. So that's quite impressive in terms of how well this works in this situation. Okay, so that's the end of chapter 9. We'll come back later with chapter 10.